Hello everyone, welcome back to my channel again. In our today's video, we will be learning the basics of coordination compounds. Okay. So what we'll be learning is what a coordination compound is. Why do we call it coordination compound? What does this term coordination means? And what are the various other terms which we use in coordination chemistry? The very common terms which we again and again use in coordination chemistry. We'll be trying to understand its meaning with various examples. So without wasting any further time, let us start with the coordination chemistry important terms used in coordination compounds. Okay, so our first important definition which we have to learn is what is coordination compound. What is the definition of coordination compound? Why this word coordination is used? So remember that coordination compounds are the compounds in which the central metal atom is linked to the number of ions, okay, or neutral molecules, or coordinate by or other groups by a coordinate bond. Now, I hope you can understand what is a coordinate bond is. We call it a coordinate covalent bond also. It's a covalent bond, but there is a difference between a covalent bond and a coordinate covalent bond. A coordinate covalent bond is formed by the donation of lone pairs by a system which is electron rich. In inorganic chemistry, we call them as Lewis base to a certain group of atoms or to a particular element or ion which is deficient of electron, which we called as Lewis acid, which can accept that pair of electron donated by the Lewis base, and then they can share it and can form a covalent bond. Usually when we say a covalent bond, what do we understand? There is one particular atom, another atom, they share equal number of electron, mutual sharing forms a covalent bond. But if there are two groups, one donates, another one accepts, that is done, and then they share it. That is coordinate covalent bond. And that is what we are trying to learn in our video, that what is this coordination compound is. So whenever we talk about coordination compound, with reference to coordination compound, the group or the metal or the element which is accepting this pair of electron is nothing but the metal atom, okay, which is usually transition metal atom, and the group or the atoms which are donating the electron pair to this metal atom in coordination compounds, we call them ligands, and they are nothing but the Lewis base. One very common example, if I'll give you to just to explain it to you, is whenever we have this particular complex, let's say CuNH3 4 2 plus, okay. So in this, what do we have is this particular copper is nothing but the central metal atom, which is accepting that electron pair from these groups, okay. Now, why nitrogen in ammonia can donate? Because nitrogen in ammonia has a lone pair of electron, okay. It's a Lewis base, which can donate to copper and can form a coordinate covalent bond, okay. As a result of which the complex which forms is nothing but a coordination complex. So remember that in coordination complex, two important thing is metal and the group which donates electron to metal. The metal is usually electron deficient, okay, and can accept electron pair, which we call as Lewis acid, and the group actually are the donors which have lone pair or have negative charge, which can be donated to the central metal atom and can form a coordinate covalent bond, okay. So that is what, or that is how a coordination complex is formed. Now what we'll try to do is try to understand the central metal atom and the definition of the ligand separately. So let us go for the definition of central metal atom and the ligands. So our next topic is what is central atom, metal atom or ligand. The metal atom or the ion to which certain atom or group, which we called as ligands, I have already told you, which are electron donors or which are Lewis base, is attached is nothing but the central metal atom or ion. So again, I am taking the same example just to clear it, that if you have this particular complex CuNH3 4 2 plus, so remember that this Cu is nothing but the central metal ion. Okay, so the copper ion is the central metal ion. This group which is donating electron to this is nothing but the ligand. As a result, they form a coordinate covalent bond, and that coordinate covalent bond results into this particular formation of the complex, which is nothing but coordination complex. Okay. Now, the next definition which we have to learn is what are ligands? Okay. So as we have already done it, ligands are nothing but atoms, ions, or molecules which are capable of donating that electron pair to the central metal atom or ion. Okay, that means they must be electron rich. They are Lewis base. They can be simple ions, you can see clearly on the screen. They can be chloride ion, you can see it can be NH3, why NH3? Because it has lone pair, or it can be big molecules like this, ethylene diamine, which you can clearly see in the screen. Okay, why ethylene diamine? Because ethylene diamine has two nitrogen, okay, which have lone pair and can easily donate it. So it is not necessary that ligands has to be a simple molecule, it can be big molecules also. Okay, so that is how actually we can understand what are ligands. Now remember that this particular ligands may have one donor site, like NH3 has one donor site, chloride has one donor site, means one atom to donate in that particular molecule. Ethylene diamine, on the other hand, two donor sites. See, two nitrogen are there to donate. It may happen that they may have three, it may happen that they may have four, it may happen that they may have 5 or 6. So depending upon how many number of groups they have to donate the electron actually to the central metal atom, depending upon that, ligands are classified into unidentate, didentate, tridentate, or in general we call it polydentate. And the term which we use, okay, the number of ligating group, to explain this term, that how many ligating group you have or how many donating group you have in a particular ligand, to explain that we use a term which we called as denticity. So what is denticity? It is nothing but the coordinating group. That is what I have told you, the atoms or the ions which you have, right? So the atoms or the ions which you have, okay, how many donating groups it has? 1, 2, 3, 4. Depending upon that, your denticity is found out. So if it has 1, we call it denticity 1 or unidentate. If it has 2 groups to donate, then it will be denticity 2 or didentate. If it has 3, denticity 3, tridentate. And similarly, you can go on. And in general, for more than 2 or 3 or 4, we can call it polydentate. Okay. Like some example I have taken over here. This is a very common actually ligand which we use in coordination compound. This is nothing but ethylene diamine tetraacetic acid. Okay. Its ionic form, actually an ionic form, we use it as a ligand, which we write as EDTA 4-. Okay. Now how it can, when it ionizes, it gives out this H plus very easily. Okay. It's a carboxylic acid. So it gives you that H plus. So it will convert into O minus, O minus, O minus, and O minus. So you can clearly see there will be 4 O minus. So there will be 4 donor. And top of that, this 2 nitrogen will have lone pairs. So this 2 nitrogen can also donate. So as a result, how many coordinating sites are there? 6. So such ligand will have a denticity of 6. What do we call it? Hexadentate ligands. Okay. We can have other type of ligand also which will have 2 donors. Okay. Like this particular one. Okay. Ethylene diamine, it has 2 nitrogen. So 2 nitrogen can donate. So it is ethylene diamine, denticity 2, or we call it didentate. We can have other anionic didentate also. This is neutral didentate. This is anionic didentate, like this oxalate ion. Okay. This oxalate ion has 2 O minus. This is O minus and O minus. So total charge we have written 2 minus. So we call it didentate ligand again. Cl minus, it has only 1 coordinating site. So it is monodentate or unidentate, having a denticity of 1. So that is how ligands are classified into different types based on their denticity. Okay. Now coming for the next, that is chelation. Now what is chelation? Remember that this is a property of a ligand. Okay, at least it has to be a didentate ligand. It can be a tridentate, it can be tetradentate. When this particular ligand binds with the metal, the condition is this particular ligand must be able to form a 5 to 6 membered ring or a ring with the metal once it donates from its 2 donors or 3 donor side or 4 donor side. Once that ring is formed, that this particular ligand will have the property of chelation. Okay, so chelation is nothing but a property where a ligand from its 2 donor side or a 3 donor side donates to the metal and forms a ring. That ring is known as a chelate ring, and the property is known as chelation. The particular complex is known as metal chelate. And if it is a bidentate ligand which is doing it, we call it bidentate chelating ligand. If it is a tridentate ligand which is doing it, we call it tridentate chelating ligand, and so on, so forth. Okay. Here I have taken one particular example. You can clearly see that I have a donor, okay, and this is donating to the metal. So once it is donating to the metal, what is happening is that this metal now actually is forming a closed ring. Can you see there clearly that this metal is forming a 6-membered ring? So this property is known as chelation. This particular complex is known as metal chelate. And since this is a didentate ligand, means it has 2 donor side, 2 nitrogen. So we call it didentate or bidentate chelating ligand. So the criteria for a ligand to become a chelating ligand is that it should be able to form a ring with the metal atom. Okay, then it will be known as a chelating ligand, and it will have a property of chelation. Coming for the next, ambidentate ligand. What is the ambidentate ligand? Always remember that, be clear, ambidentate ligands are unidentate ligands, but having more than one coordinating. Okay, they are not didentate, they are not tridentate ligand. They are unidentate. They form only one bond, but have more than one sides to form one bond. For example, you can see on the screen, okay, what we are taking is the first one, the nitrito N and nitrito O, which we are writing, okay. This is NO2 minus, okay. NO2 minus has this structure O minus, okay. O will have O minus and double bond O. Now this O minus can donate its electron pair to the metal and can form and can act as a ligand, okay. We call it nitrite, right? In coordination complex, we call it nitrito. Bonded with O, we call it O nitrito, okay. But the same thing can donate through this nitrogen also, not at the same time. Both will not donate. It's not a didentate. But if oxygen will not be able to donate, this nitrogen can also actually will donate. And you can see over here. See, nitrogen is donating now, not the oxygen. So the same ligand has 2 sides to donate. So we call it ambidentate. Same way, we have a thiocyanide, which we call as thiocyaneto. Sulfur is donating. The same ligand, nitrogen can also donate. So the unidentate ligand, which have more than one coordinating sites, are known as ambidentate ligand. Okay, very common and very important also in coordination complex. Coming for the next, that is coordination number. What is coordination number? In very, very simple words, it is the number of bonds which a metal forms. If a metal is forming 4 bonds with the ligand, it is the coordination number 4. If a metal is forming 6 bond, coordination number 6. If a metal is forming 5 bond, coordination number is 5. Okay, so depending upon the number of bond which a metal forms, that is known as the coordination number. Don't make a mistake. Don't write it as the number of ligand which a metal is bonded with. It's not the number of ligand. It's not always true. It is true when the number is actually the unidentate ligand. It is the number of unidentate ligand which a metal is bonded to. That is very much correct. But don't go with number of ligands. Sometimes you may go wrong when there is a didentate or a tridentate ligand where one ligand itself can form 2 to 3 bonds. So the very correct definition of coordination number is the number of bond which a metal can form. Simple as that. Okay. Is nothing but coordination number. Like I have taken one example over here. You can see clearly cobalt. Cobalt is forming how many bonds? 6 bonds. You can see clearly 4 with ammonia and 2 with chloride. So number of bond is 6. So coordination number is 6. Okay. So if it is 5, it will be 5. If it is 4, it will be 4. So see the number of bonds. Okay. Coming for the next, that is coordination entity. What is coordination entity? The way to write a coordination compound is, whenever we write coordination compound, we always enclose that in third bracket. What we enclose in third bracket is two things, the metal and the ligand. The ligand, which is directly attached to the metal, is enclosed in third bracket. So that together, that collective, metal and ligand, when it is enclosed in third bracket, that collectively we call it coordination entity. So anything which is written third bracket, that means the metal and the ligand is collectively termed as coordination entity. Okay, which you can see as the example CuNH34. So that total, whatever is written in third bracket, is coordination entity. NiCO4, which is written in third bracket, that means carbon monoxide is forming bond with nickel, coordinate covalent bond. That is nothing but coordination entity. Okay, coming for the next, coordination polyhedra. Okay, it is nothing but the special arrangement. Special arrangement basically means the arrangement in space. What kind of geometry it gives you. That coordination entity, okay, whenever the ligand approaches to the central metal atom, it approaches from a specific direction. It is direction. It has a it is directional in nature. Okay, so that direction which you get gives you an arrangement in space. That arrangement gives you the geometry. So basically, it's the geometry of the coordination entity or the coordination sphere. Okay, so that geometry which you get or arrangement which you get is nothing but coordination polyhedra. It can be octahedral, it can be square planar, it can be trigonal bipyramidal, trigonal pyramidal. Okay, it can be tetrahedral. So all this special arrangement which you get is nothing but coordination polyhedra. Okay, like over here you can clearly see the geometry which it getting is octahedral. So that is the special arrangement. Okay, the 6 ligands are coming from the 6 ends of a octahedral. Coming for the next, oxidation number, a very, very important topic in coordination compound. Very, very important. Okay, what is oxidation number? It is nothing but the electrical charge of the central metal atom. Oxidation number is always for the central atom, which it has or appears to have when it binds with the ligand. Sometimes it appears, okay, sometimes it already has a actually charge. That particular charge is nothing but oxidation number. Now, a very important point is, how do we know what is the oxidation number? How to calculate the oxidation number? Very, very important, because whenever we write name of coordination compound, whenever we write formula of coordination compound, okay, whenever we want to understand the configuration of coordination compound, configuration of the central metal atom, oxidation number plays a very important role, because while writing nomenclature, we need oxidation number. While writing the formula, we need oxidation number. While understanding the total charge of the coordination sphere, we need the oxidation number. So without knowing oxidation number, we cannot go ahead in coordination compounds. So let us learn how to calculate oxidation number. Okay, so calculation of oxidation number. So how to do it? Let me take some examples and help you. Okay, so let me take that simple example which we have taken. The first example, CuNH3 4 2 plus. Okay, let me take this particular ionic complex and help you to calculate the oxidation number of cobalt. How to do that? Now try to understand, we don't know what is the oxidation number of cobalt. So what will be our solution is, let the oxidation number, I'm writing ON, okay, oxidation number of CuBx. I don't know what is it. What is the charge? I don't know. So I'm taking it as X. Now always remember that if I sum the charge of the metal and the ligand, it has to be the total charge. It has to be equal to the total charge on the coordination entity or the coordination sphere. So copper is X, ammonia is a neutral molecule, NH3, right? It does not have any charge. So into 0 equal to, what is the total charge? Plus 2. So what is X? X is equal to plus 2. So how or in what form copper is present in this complex? Copper is present as Cu2 plus, as cupric state. So what is the oxidation number? 2 plus. Okay. Let me take another complex. Second one. Let's say FeCN6 3 minus. Let me take this. Let us calculate the oxidation state of iron. So again, I don't know what is the oxidation state of Fe. So let the oxidation state of Fe be X. So X plus how many ligand? 6 of it. What is this? Cn. Cn minus cyanide. Okay. So it is -1 will be equal to, what is the total charge? -3. So X minus 6 will be equal to -3. X will be -3 plus 6, which will be +3. So iron is present as Fe3 plus, ferric state of iron. That is how we calculate it. Very, very important, very clear understanding must be there for to calculate oxidation number. Okay. If you have a very clear idea of calculating oxidation number, it will be very, very easy. Okay. And you have to know the charges on the ligand. So know that which ligand is anionic, which ligand is neutral. So you need to know that. Let me take some more example just to help you, like NiCO4. We call it nickel tetracarbonyl or tetracarbonyl nickel complex. Okay. So if I take this is a neutral complex. Okay. So I don't know the oxidation number of nickel. So X plus 4 carbon monoxide 0 CO. It's not cobalt. Okay. It's carbon monoxide. So CO is 0. It's a neutral molecule. Will be equal to, what is the total charge on the coordination sphere? 0. It's a neutral. So X is 0. What does that mean? That means nickel is present as nickel metal. Okay. It is in ground state. It is not present as in ionic state. Okay. Let me take another one. Let me take nickel complex only. Okay. Like NiCN4 2-. So again, nickel, I don't know, X, cyanide 4 into -1. What is the total charge? -2. So X will be -2 plus 4, which will give me +2. So nickel is present over here as Ni2 plus C. Different complexes, different oxidation states. Okay. So depending upon the complex, the oxidation state will vary. Okay. So that is how actually we calculate the oxidation number of various metal ions in a complex. So the only thing which you need to know is what is the charge on the ligands, what kind of ligand it is, what is the charge it carries. Okay. So these are some of the examples. Okay. There are numerous examples which you can try. Okay. So that is how actually we can understand the basics of coordination compounds. Okay. So that is all about the basics of coordination compound. Okay. What are ligands, what are metal, what is coordination bond, what is coordinate covalent bond, what is denticity. So all these things we have learned in our today's video. Okay. A very, very important topic from coordination compound. So thank you, everyone. Do subscribe for this channel for explanation on various topics in chemistry. So thank you.